Let's see. Yeah, we're still lined up. That's good. All right. Inner chapter A is, here we go. So we're going to start off with the basic systems for naming organic compounds. We've been sort of introduced to it with chapter 1. We've got a smattering and some of the generalized rules for drawing and naming side groups. And I've sort of introduced you to the IUPAC system, and I hope your general chemistry class also emphasized the fact that these names aren't just arbitrary. They have been developed by this IUPAC group or a subcommittee of it to do one of two things. Actually, do two things. The name should be unambiguous. What we mean by that is it can't be anything else but that compound, both in terms of its connection of atoms and their three-dimensional structure, right? And we're going to get into that more so in organic chemistry than we did in general with the three-dimensional arrangement. So the name has to be unambiguous. In other words, you can go from the name to writing the compound, or you can go from the compound and write the name. And we don't want it to be redundant, non-redundant. That is, we don't want to say something twice in a molecule's name. Example from inorganic chemistry is, well, name that, right? We know that it's I teach it as a type 1 compound. In other words, the metal, the first part of the name, is from a part of the periodic table where the metal can only have one charge. None other is possible. Sodium is an alkali metal. It's always +1. So all we have to do is say sodium chloride. And we know that the halogens are always -1. So this is both unambiguous and non-redundant. And when I give my students a test, I'll give them something like this. And one of the multiple choices will be sodium 1 chloride, right? Because this is how you tell the charge on a metal that has the potential for multiple charges, like a transition metal of some kind. That's wrong because it's redundant. We don't need it. Okay. So those are the two basic rules for naming compounds: unambiguous and non-redundant. Now, these examples here, these would be considered trivial names. And a trivial name doesn't mean it's less important. It just means it's not standard. So vanillin is that structure on the left, right? Geraniol, azulene, morphine, right, is an extremely complex molecule, but it's a product of biochemical reactions, right? It's enzyme mediated, and enzyme mediated reactions do two things that inorganic catalysts don't do. Inorganic catalysts are not selective. In other words, the catalyst works the same forward and backwards, whereas enzymes tend to work only one direction. So if you want the reaction to come back the other direction, you need another enzyme. That's one of the ways that living systems control the biochemical pathways, is with these selectivity of enzymes. And some enzymes, in fact, most enzymes, can be activated or deactivated. So they can be sitting there and they need a signal to activate them, which inorganic catalysts can't do. Okay, I digress again. Okay, so here are the basics. We're going to start off with really, really simple alkanes. An alkane is composed of carbons and hydrogens only, with no functional groups. So we often call them straight chain or linear alkanes, although we know that straight means zigzag. So the rules for naming them, the name always ends with ANE. Whatever we put in front of it, it ends with ANE. And we go by counting the number of carbons, right? So if we have a number of carbons, we can have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We'll go down to 10. The first one is meth. So we end it with methane. That's one carbon only. The second one is F. And so this would be ethane, methane, ethane, propane. My guess is that these prefixes were sort of grandfathered in from the Dark Ages. The fourth one is butane, right? That's the same stuff that you find in lighters, butane. Now we get to the more organized part of the naming convention, and we go back to the Greek prefixes. 5 is pent, pentane. 6 is hexane. 7 is heptane. Okay. 8 is octane. That's the one that's in your gas tank. And 9 is nonane. And 10 is decane. Now you can go a lot higher than that. And let me see if, no, okay. So we're only going up to 10 here, I think. Yeah. So the structure here in simplified form would simply be, well, this one obviously we would say CH4. This one we could say either we could say CH3, CH3, or we could just draw a straight line, right? And there's a carbon on the end of that. This is the bond. Propane is going to be like that. Butane is going to be like this. 1, 2, 3, 4. Pentane, 5. 1, 2, 3, 4, 5. I have to count them so often. 6. 7. 1, 2, 3, 4, 5, 6, 7. Remember, each one of those kinks is a carbon, and we have to have enough hydrogens on there to make 4 bonds. But they're all single bonds between the carbons. And then I'm going to leave the rest of them out. It's just takes too much time to draw all of them. But you should have the right number of carbons. And don't forget that at the end here, if it has no other element there, that's a carbon. Right? So if I were to take heptane and change this to OH, now that would be based upon what? 1, 2, 3, 4, 5, 6. That would be based upon hexane. And it would be hexanol, just as a teaser. So if there's nothing written there, it's a carbon. Okay. Now, if we substitute anything in positions, and they're using a generic G group here. If we substitute them someplace, then we have to prefix the name with whatever that substitutional group is. And we also have to say which one of the carbons does it occur on. So you have to learn how to number the carbons. If we're just like this, it doesn't matter. You start from the left or the right. It's 6 of one, half a dozen of the other. So this would be 1, 2, 3. I mean, if we were doing it this way, 1, 2, 3, 4. And we could go all down 1, 2, 3, 4, 5, 6, 7. That's when it's not substituted. When you substitute it, you consider where in that chain the substitution occurs. And I think that should be on the next slide. Yeah. What you want to do is number it in such a way that the number assigning the attached group or atom on the side is the smallest possible. So if we were to put a chlorine here, that would be the second carbon would be 2-chloroheptane. Okay, it wouldn't be 1, 2, 3, 4, 5, 6, 6-chloroheptane, because 2 is smaller than 6. Okay. If we put it on the end, we would say 1-chloroheptane. Now, what if we had, well, their example here is propane. So 1-chloropropane or 2-chloropropane, those are different compounds. Those are different molecules. But if we put the chlorine on the 3, is that different? No, we've already named that one. All you have to do is take 1-chloropropane and flip it around. And that's the same as putting the chlorine on the 3rd carbon. But now you have to name it from that first one. So you really only have 2 possible conformational isomers, they call them, of chloropropane. It's either 1 or 2. If you put it on the 3rd one, it's the same as putting it on the first one, because you just flip it around and you got the same molecule. Okay, so how to name them? Identify the main chain. The main chain or the parent chain is the longest unbroken chain. So if we had something like, let's take hexane. 1, 2, 3, 4, 5, 6. And we substituted a methyl side group on it somewhere. So I'm going to put a methyl here, right there. The longest continuous chain is this one, 1, 2, 3, 4, 5, 6. So we know that it has to end with hexane. And we have to number it so that this side group, this methyl group, has the lowest number. So we number it from this end, 1, 2. So we'd have 2-methyl hexane. Okay. If we put it, let's see, what if we moved it to here? So 1, 2, 3, 4 is only 4 carbons. 1, 2, 3, 4, 5, 6. It's still hexane. But what if we changed it to a propane subgroup? Let's put a propane here. So let's say 1, 2, 3. 1, 2, 3. And that's bonded to this carbon. So if we went 1, 2, 3, 4, 5, 6, that would be 6 on this chain. But if we went 1, 2, 3, 4, 5, 6, 7, that's the longest chain. So now it would be heptane. And the side group would be on the shortest, 1, 2, 3, 4, or 1, 2, 3, 4. Doesn't matter. Either way. So it's 4-ethyl heptane. Okay. I understand it can twist your head around 3 times once you really start getting some complicated molecules. Maybe that's why organic chemists are nuts. Everyone I've ever known is just wacko. I know they keep lousy, filthy kitchens. Their chemistry labs are the filthiest I've ever seen. I don't know how they managed to do it without contaminating their reactions. But they're more like chefs than they are scientists. Really? Okay. So we have the substituent, which is the side chain. And we've learned how to count the longest chain and decide what the locator number is. And we don't put any, let's see, no spaces should appear in these IUPAC names. So it looks like I put a space there, but there shouldn't be a space. Ethyl heptane is one continuous word. And the prefix with a dash tells you what the substituent is. Okay. Now, the other example over there on the right-hand side, if you say, if you make a brominated methane, does it need a number? No, because there's only one carbon. That would be redundant. So we don't say one bromomethane, we say just bromomethane. Okay. Let's see. How about iodoethane, that bottom one? Right, that doesn't need a prefix either. Right, because if you put it on the 1 or you put it on the 2, it's the same molecule. Right. Now, what if, while we're at it, we're probably going to get a slide on this anyway. But if we took that ethane here and we put a bromo here, and say we put a bromo on this side, how would we name that? Well, we know that it's going to be ethane, and we know it's going to be a bromo, but it's going to be 2, so we need a prefix. Dibromoethane. Now, okay, I just created a problem for myself. This dibromoethane is not the same as this dibromoethane. So in that case, we would have to specify. This dibromo implies both bromines are on that carbon. But if I put them on separate carbons, now I would have to say, excuse me, I would have to say 1,2-dibromo. That shows they're separated. I think that's the way it goes. Either that or I'll be proven wrong in the next slide. Okay, name this one. What's the longest chain? 1, 2, 3, 4, 5. 5 carbons is pentane, right? So we would start numbering from the right-hand side. So 2-nitropentane. Where is it? So we have to learn what the constituents are named, the side groups. NO2 is a nitro group. Yeah, there it is at the bottom, 2-nitropentane. All right. Oh, because we want the smallest number prefix. Yeah. We numbered from the right to the left this time because it gives us a smaller number. Or, I mean, if you prefer left to right, just take the molecule and go, poop. Okay, now, here's a disubstituted one. All right, now how are we going to deal with this one? The one on the left has a 2 and a 3 substitution. So we want the numbering to give us the smallest possible numbering for both of them. So if we numbered from the right, they'd be a 4-5. If we number from the left, they're a 2-3. 2-3 is preferable to 4-5. On the right-hand possibility, the first two substituents would be on the 1, rather than those two substituents being on the 2. So are they going to give us a name for one of those? Oh, these are the Greek prefixes. You probably already learned those in general chemistry. Di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. Left out mono for 1, but we probably don't use 1 because that would be redundant. So you need 1, let's see. Write the name of each of the substituents as a prefix. Add the multiplying prefix if necessary. When there are 2 or more of the same substituent, write the appropriate multiplying prefix just before the name of the substituents. So like we did here, dibromo. So we know there are 2 bromos, but we have to say where they're located, and then add the locator number for each substituent. So here we have a more complicated molecule. All right, let's see if we can find the longest chain. I'd start at the 2 fluorines on the left, because the nitro is out there on the left. So the first carbon is attached to the nitro and the 2 fluorines. So that's 1, 2, 3, 4, 5, 6. We've got hexane is our longest chain. Hexane is the parent chain. Okay. Now we've got 2 nitros and 4 fluoros. So we've got tetra, fluoro, put somewhere in here, and we've got di-nitro. Okay. Now we have to decide, the rules have to tell us which one comes first and how do we name them? How do we put their position? Well, let's see, we got to number it too, right? So it's hexane. Go 2, 3, 4, 5, 6. Yeah. So this is, I don't know which way to number it yet. How many carbon atoms? The longest chain, we got that done. Which end of the carbon chain should numbering begin? Well, I don't know that yet. How many carbons? We got that, hexane. So the author numbered from the left-hand side. Are they going to explain that? What are the names of the substituents? Fluoro and nitro, we got that. Oh, okay. So which one gives us, notice that we've got, I better draw them in here. So we've got a fluoro here and a fluoro there, and we've got a nitro here. Then we've got another fluoro here, and we've got a nitro here, and a fluoro here. Okay. So I think what's happening here is the most number of substituents with the lowest number of prefixes would be this one, because you've got 3 substituents on that 1 carbon. So we're going to start numbering here 1. Like that. So this is going to be, for the fluorines, it's going to be 1, 1, 3, 5. 1, 1, 3, 5 tetrafluoro. And the dinitro is going to be 1, 4. Okay. Now, which one comes first? Let's see, prefix. Did we get that rule? Which one comes first? It's alphabetical. So F comes before N. Right? Yeah, it's alphabetical. So we put this one first here, and then we say this one second, hexane. And we put dashes in between the substituents. So we put a dash here between those two. And the dinitro would be contiguous with the hexane. Is everybody confused yet? No? So far, so good. Okay. Get a fresh marker. Uh-huh. Okay. Let's see. What if there is a locant number tie? Okay. So we've got fluorine on one end of this one propane and bromine on the other end. So we number it not only based upon the smallest number possible, but since it's a tie, we go by alphabetical. So we number it from the B side rather than the F side. 1 bromo, 3 fluoropropane. I wouldn't want to have to be on the committee that came up with these rules. You'd have to be a real fanatic. Okay. Alkyl substituted branched alkanes. Okay. So if the branch happens to be an alkane, then we have names for those. What we do is when it becomes a substituted form, we change the A and E to YL. So it's methyl, ethyl, propyl, butyl, pentyl, hexyl, so forth. If it's a substituent, a side group, a branching group. Okay, so in this case, we have a methyl branch at the 3 carbon, and that gives us the lowest possible number. Rather than 1, 2, 3, 4, rather than 4 methyl, it's 3 methyl. Propyl. Now, when we have other substituents in there, we have to number it based upon the alphabet. So chloro, C comes before P. So that means we have 4,4-dichloro instead of 1, 2, 3, 4. Instead of 5,5-dichloro, we have 4,4-dichloro and then 5-propyl. Okay, so the alphabet wins. Okay. Now they tell us, apply caution when numbering. The way in which a molecule is drawn can influence your perception. Okay. We actually looked at one possibility like that before, where we had a big branch. And sometimes you just have to check out each possibility and say which one gives you the longest chain. At least that's the way I do it. Okay. So, incorrect for this first one. 1-methylpentane. Well, actually, it's not a branch because if you follow the longest chain, you've got hexane. It's drawn wonky. Instead of a proper zigzag, it took the zig and went zag with it. Right? The second possibility, the incorrect one is 2-ethylbutane. So if we follow the other chain, we got 1, 2, 3, 4, 5. So it's pentane, actually. So we say, what gives us the smallest number for the pentane? It doesn't matter. Number it from either side, and you still got 3-methyl. Okay. What if we get an alkyl substituent group that's also branched? Let's see. Identify the main chain. That's always the case. And assign the root name. Then number the carbon atoms of the branched alkyl group's main chain. And in fact, what you can do is, so that you don't get lost in where you are and what you've determined as the longest chain, you can go ahead and number it arbitrarily. You may find out later that it needs to be numbered the other direction, which is fine. But at least you won't get, you won't set your longest chain aside and forget which one it is. Then add prefixes and locator numbers. Let's see. Okay, so for this example, actually, I like the second example better. For that longest chain is butane. Excuse me, it's ethyl dimethyl. Oh, we're just talking about substituent groups here. Okay, so what they're saying is that this slide is giving you substituent groups that are going to be attached to a main group later, right? So you have to also apply the rules to the side group, right? Which is the longest in that side group, that bottom group, right? The longest chain there is 1, 2, 3, 4. Now, that doesn't make any sense. Oh, yes, it does. Yes, it does. Because see the squiggly line? That's where it's attached. So you start from the attachment point, and that's your number 1 carbon. Okay, now it makes sense. And then you go whichever direction gives you the longest chain. And in this case, it's 4 carbons long. And at the first carbon, you have an ethyl branch. Second carbon, you have a dimethyl. And the rest is the butyl group. And you still, now in this case, we're constrained by the number 1 carbon is the one that's attached as the substituent. Right? So we don't have the luxury of saying that carbon up there is number 1, and we're attached at 2. We're automatically attached at number 1, always. Okay, did I say that right? Okay, let's create something. Let's see that squiggly line. Let's just create something. Let's say we have this one like that. 1, 2, 3, 4, 5. Say we've got pentane. And we're going to attach that side group right here. Okay. Wait a minute. That's okay. Let's make it longer. So we'll be sure that this is our main group. Right? I don't want to draw something and say, wait a minute, that substituent group is part of the long group. Okay, so now we are attached here, and we're going there and there with this branch. And this is the number 1 carbon right there. By default, wherever it's attached is the 1 carbon. And then we go 1, 2, 3 more. There, like that. And then on the second one, we have 2 methyl groups. So here we have an ethyl group is 1 ethyl. And here we have 2 dimethyl butyl. So that's the substituent on top of this one. And since this one is attached closer to this end, it's attached at the 2 group. So we put this in front of, we put 2 here, saying this group is attached at the 2. And then on the end out here, we write 1, 2, 3, 4, 5, 6, 7, 8 octane. Okay, so this says at the 2 position on octane, we've got this side group attached. See, it can get messy pretty fast. I guess that's why they need all the rules. Okay, incorporating branched alkyl groups into an IUPAC name. This is probably going to answer the questions I was trying to do there. Yes, in parentheses you put the substituent group, and you precede the parentheses. I forgot my dash. You precede the parentheses with a position where it's attached to the main group. That's just going to take practice, and I'm rusty too, because I only do this in the summer. Okay, cyclic compounds. These are all the alkanes. So far, that's all we've talked about. Just the straight chains, none of the zigzag chains. But you can, better leave this one here. In order to name a cyclic group, you count the number of carbons in the cycle, and you go back to the ANE name. So let's say we have 5 carbons in a ring. Okay. If it were a straight chain, it would be pentane. But since it's reached around and grabbed its tail, it's a cyclopentane. Okay. Just how many carbons? Propane, cyclopropane, cyclobutane, cyclopentane, cyclohexane. If you look on a can of shaving cream, for instance, you'll find in the ingredients, one of them might be cyclopentane, or it might be, well, another one, the possibility is an isobutane or an isopropane. But sometimes they put cyclos in there. I think they avoid cyclos because they're more expensive to create. But it's possible. Does anybody read ingredient labels? No? I don't know what that is. Very few of my students read labels. I mean, that's all I do when I go shopping. I like to read labels, see what's in there. When you read a label on anything, whether it's edible or not, the order of ingredients is major, less major, minor, 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 minor. So the highest concentration is the first one. Okay, so if these are going to be side groups, say this is attached to something else, right? Whatever it is, then it becomes cyclopentyl. That YL ending, just like the alkanes. Methyl, ethyl, propyl, just put a cyclo in front of it. You can't have a cyclomethane, right? You can't cycle 1 carbon. You can't cycle 2. You can cycle 3. It's not very stable, but you can cycle it. Cyclopropane. Someone's cooking. Smell that? Smells a little like grease, like fried chicken or fried fish, something. What time is it? Oh, lunchtime. Somebody's heating something up in the microwave. So So what you have to do next, if you have a cyclic part to a compound, is decide, is the cycle the main part of the molecule? Does that become this part over here? Is it cyclopentane and then something else substituent? Or is it the ill? Is it a side group? That's what we have to decide next. Distinguishing between the ring carbons and the chain carbons. So first of all, when you're counting carbons, you don't include the ring carbons in the chain count. So that first one you see, you count 8 carbons. So that would be octane. The cyclopentyl group has fewer than 8 carbons. So it becomes a substituent. Okay. And on the second one, we find that the longest chain there that's not cyclic is 1, 2, 3, 4, 5, 6, 7 carbons, whereas the cyclic is cyclooctane. So it has 8 carbons. That means it is the main chain. So cyclooctane is the root, and then the rest of it is the substituent. So in this case, we have to attach the 1-methylhexyl, right? That number 1 carbon means that there's a methyl group attached to it. 1-methylhexyl is the substituent, and then cyclooctane. Now, why don't we have to put a number in front of the 1-methylhexyl to say where it's attached? Because it doesn't matter where you attach it. It might as well be 1 all the way around, right? Now, if you have another group on there, then it would matter. Okay. Numbering system in cycloalkanes. C1 has the greatest number of attached substituents. All right, so if you have a carbon, if you have 2 of the carbons in a cycle that have substituents on them, then the number 1 is going to be the one with the greatest number of carbons attached to it. And then you have to decide, are you going clockwise or counterclockwise for the next substituent? And there, the decision is between which one gives you the smallest number, right? If you start with the greatest number of substituents, and that's 1, then if you go this way and it gives you, say, a 3, but you go this way and it gives you a 7, then you go clockwise to the 3. They're going to give us an example? Yes, they are. Okay. So we know that this one is cyclohexane, right? 6 carbons in the ring, and the substituents don't have more carbons than the ring does. So we have cyclohexane as our main group. Okay. Now we have which one has the most attachments to it, substituents, the top one. So that becomes number 1. That's 1. And we have a bromine here, and we have a chlorine here. Okay, which one would give us the smallest number? This way would be 1, 2, 3, 4. This way would be 1, 2, 3, 4. So did I count that right? 1, 2, 3. 1, 2, 3. In this case, I think the alphabet breaks the tie. So we would go this way. So it'd be 1, 2, 3. It would be 3 bromo, 4 chloro. And well, 1 would be 1, 1 dimethyl. Dimethyl, 3 bromo, 4 chloro, cyclohexane. Now let's see if I got it right. Or if the author agrees with me, let's put it that way. Okay, I numbered the right direction. left to right, 3-bromo. Oh, and then when you name it, you go back to the alphabet. So instead of putting in numerical order, you say, let's see, sure I got room here. 3-bromo, B, C, M. 4-fluoro, and yeah, 1,1-dimethyl. 1,1-dimethyl cyclohexane. So we had several decisions to make there. Which way to number it, and then when we actually write it in the name, which one comes first? And that's alphabetical. Okay. So let me see. Well, I don't have my hard copy with me. Yeah, I do. Here it is. I should keep this going so I got some others in here. Decide whether to use these handouts or not. Might be too much information. Let's see, going to ethers and alkoxies. Okay, we're close. You're seeing how far we were from the end. Okay. Now, an ether, by definition, is an oxygen bound on both sides with two groups. They can be the same or they can be different. That's an ether. But how we name it is not necessarily ether. If we call it an ether in the name, that's generally considered a trivial name. What we do instead is we go back to our naming convention. We find the longest carbon chain. So that'd be one side or the other of the oxygen. And then we name the connection here as an alkoxy, an alkane oxy something. So methoxy or butoxy, whatever the case may be. So again, we establish the root. And for this, the trivial name dimethyl ether, that first one, doesn't matter which side you start on, you got the longest chain is a single carbon. So we're going to go to methane. And then we attach to that methane a methoxy group. So methoxymethane is dimethyl ether. Right? If we were to do this, right, that would be dimethyl ether or methoxymethane. That's the systematic name, the IUPAC name. If we have diethyl ether, right, instead of methyl, we have ethyl groups, so CH2, CH3 on either side. Then the longest group is ethane. So we have ethoxyethane. Okay. The last selection there is we look for the longest grain. The propyl group would be the straight chain, but the 6-membered cyclohexane would be the longest chain. So the cyclohexane would be the root, and then we would attach a propoxy to it. Right? The propyl group with an oxy on the end is where the attachment occurs. So propoxy cyclohexane is correct. Now, the trivial name would simply say, okay, the ether's got two side groups. One of them is cyclohexyl and the other one is propyl. So cyclohexyl propyl ether is a trivial name for that. And it's like, what is the proper IUPAC name for this molecule? That's dihydrogen monoxide, right? Otherwise known as water. Okay, ethers that require locator numbers. All right. If you have a, let's see. If you have the possibility of placing the oxygen connector at multiple points in the main group, in the main chain, then you will have to put a locator number. So the first one, the methoxy occurs on the first carbon. And the second one, it occurs on the second carbon. So 1-methoxy versus 2-methoxy propane. What if you have more than one ether? Well, in the third one on that top row, you have the longest carbon chain is in the cyclohexane. So cyclohexane is your main chain, your main group. And then you have an F-oxy attached at 1 and 4. And since they're opposite one another, it doesn't matter which way you number them. They're going to be the same. So you just say there's one attached at 1 and there's one attached at 4. So it's 1,4-di-ethoxy. Okay. Now we get a little more complicated. We're going to throw in some chlorines. So the longest chain obviously is 5 long. So that's pentane. And we want the, let's see. In this case, we need a hierarchy, right? Because if we say M and C, that reporting them that way, oh, no, that's right. Because if we number from the right, that gives us the smallest numbers. Yeah. 2 and 3 versus 3 and 4. Right. So that breaks the tie. Number from the right. And then you do alphabetical. So you've got 3,3-chloro comes first because it's alphabetical, C for chloro, and M for meth comes second. And then the last one is a bear. So our longest chain or longest sequence of carbons is pentane, cyclopentane. So we got to decide which way to number, right? Which one has the largest number of groups? Well, the way it's numbered, 1 does, but 3 also has the same. But since methoxy is in the middle, it doesn't matter whether you start with the one at the top or the one on the lower left. You still get the same numbering sequence, right? Whether you go clockwise or counterclockwise. But you start with the one that has the largest number of substituents, and that's either 1 or 3. And since this molecule is symmetrical, you can start on either one. But in that case, we got to break a tie. They both start with M, right? They both start with M. So which one comes first? Methoxy or methyl? I don't know. Why did methoxy come first? Takes a higher priority. I'm sorry. It might, yeah. O comes before Y. Yeah, that makes sense. And until we learn different, that's the rule. Okay. Oh, now we got a couple slides on trivial versus common name. Trivial or common names. I like trivial better. It's easier to remember. there are some older scientists that have been around for years and not retired yet that still use the trivial names. And I do it sometimes too. Right? I'll say acetic acid instead of that of ethanoic acid. Let's see, one other one that I like. Instead of molar mass, sometimes I say molecular weight, because that's the way I used to learn it. Okay, so isopropyl, iso. Okay, if we're going to have an alcohol, and we start with the propane, where can the OH go? The OH can either go on this carbon, which is the same as that one, or it can go on this carbon. Right? Those are two possibilities. Well, this is the trivial name for this one is normal propanol. Right? The IUPAC name would be 1 propanol. For this one is isopropanol, is the trivial name, but the IUPAC name is 2 propanol. Okay. And then if you attach the substituent, if this is a propyl substituent and you attach it at the number 2 carbon, it's isopropyl something something. Tertiary butyl. Okay. And this is iso means that there are 2 carbons attached to that one. Normal means straight chain. But if you have 3 attachments to the point, say we have we got a carbon here, we got carbon here, carbon here, carbon here, then this is tertiary. That's a tertiary group. So you could put tertiary butyl, you could put tertiary, couldn't put propyl, it wouldn't work. Tertiary pentyl. Primary, secondary, tertiary for kinetic reactions. Right. Tertiary elementary reaction step requires that 3 reactants come together at once. It's very unlikely. So tertiary steps are not. Am I running out of time?
No.
Oh, okay. Just organizing. Or